Alright, so this is a recording for our missed class that the university requires us to provide. Okay, so I said alkanes are usually not reactive. If they have to react, you have to use very harsh conditions because they are fairly inert. Alkanes are fairly inert. So they can be oxidized and chlorinated or halogenated, so to speak. So you can add oxygens or you can add halogens on the alkanes, though you might need harsh conditions. I told you what oxidation is. Okay, so it could be the loss of electrons. It could be increase in oxidation number because you're losing electrons. Reduction will be gain of electrons or decrease in oxidation state. So there's one shortcut you can use called oil rig. So oxidation is loss of electrons, reduction is gain of electrons, oil rig. Okay, if both of them happen together, if oxidation and reduction happen together, we call that reaction redox reaction. But there is a calculation that you can do to determine if the carbon of the alkane is oxidized. You just calculate the number, you just determine the oxidation number on the carbon. So if the number goes up, you're oxidizing. If the number goes down, then you are reducing. And you can read all that text. I'm just summarizing. So to determine the oxidation state, what we also call oxidation number, each carbon will take a value of 0. Each hydrogen takes a value of +1. Each single bond to an electronegative element like oxygen, nitrogen, or halogen will take -1. Remember, halogens could include chlorine, fluorine, iodine. Those are halogens and bromine. So that's the rule. But if it's doubly bonded, then you're gonna multiply by 2. So for example, for this carbon, this oxygen will be -1 by 2 because each oxygen is -1, but there's a double bond. So you simply pretend that carbon is bonded to 2 of them. That's how it becomes -2. Okay. Now let's look at an example. What is the oxidation state of the carbon in the center? So that the oxidation state of that carbon is going to be equal to the negative of the sum of what is outside. Okay, so remember each hydrogen is plus, so you get a plus, 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 plus. So the oxidation state of the carbon in the middle is going to be equal to the negative of the sum of the numbers that are outside, the values that are outside, which is 4 plus 1s, so it's -4. And that makes sense. This has to be -4 to neutralize the +4 that's outside to make the whole molecule neutral. Okay, what about this carbon? Remember, each electronegative element, En is electronegative element, will take a value of -1. So the oxygen is -1. And we don't consider this guy because it's not directly bonded to the carbon in question. The hydrogen is +1s, so it's again the oxidation state of the carbon at the middle will be the negative of the sum of what's outside. The answer is -2. For this one, chlorine is electronegative. It's by itself -1. So the oxidation state of carbon is the negative of the sum of what's outside. Again, you get -2. For this one, nitrogen is electronegative, takes -1. Oxidation state of that carbon will be negative of the sum that's outside. Again, it's -2. Okay. So that's how you determine the number in the middle. If you are doing the oxidation state for this carbon, then the elements directly bonded to it are this carbon and the hydrogen. The carbon itself takes an oxidation number 0, according to this rule. So you have negative, you always put the negative, the oxidation state of the carbon in question will be the negative of the sum of what's outside, which is plus 1 and 0. So that carbon is negative 1. For this carbon, oxidation state will be the negative of the sum of elements directly bonded to it, which is the hydrogen, and the carbon. So it's negative 2. For this one, what's bonded directly to it? This hydrogen, and a carbon. So everything is added. Get the negative of what's added is negative 3. Okay. If you have it multiply bonded, you would pretend that those elements are separate. Like this double bond will in theory is 2 oxygens bonded to the carbon in question. Same to this double bond to this oxygen. So I just opened it up. You could take all these to be negative 1s. Alternatively, just know this is negative 1 times 2, giving you negative 2. So what's the oxidation state of the carbon in CO2? Sum up what's outside, do the negative of that. So negative of what's outside, negative 2. You know, if you do negative 2 plus negative 2, it's going to give you negative 2 minus 2. So the negative of negative 4 is plus 4. So that carbon bears a charge of plus 4. For this carbon in the middle, it's directly bonded to the hydrogen, the oxygen, and this doubly bonded oxygen, which I could easily draw it like this. So I have plus 1, I have negative 1, negative 1, negative 1. Okay. So what we do here, you add what's outside. Add what's outside and then do the negative of that. So it's negative 1, negative 1, negative 1, plus 1. Alternatively, we say negative 2 plus negative 1 plus 1. Whichever way you do it, you're going to get the answer as negative 2 in here. The negative of negative 2 is plus 2. So this means that this carbon in CO2 is highly oxidized compared to this carbon in methanoic acid. So what about the one inside? Again, this carbon right here can easily be taken to be bonded to 2 oxygens in theory. So that's where the negative 2 comes from, because the double bond you get negative 2. Sum what's outside, negative of what you summed, answer is 0. Okay. So if you're moving from here to here, what are you doing? The number is going down. That's called reduction, because the oxidation number is decreasing. If you're going the other way around, you'll move from oxidation 0 to plus 4. That's called oxidation. That's why I told you, think of oil rig. When you lose electrons in oxidation, you gain the positive number. So here, do the same thing. The carbon in question will be negative 2. Here, the carbon in question will be negative 4. Going this way will be reduction. And it's very obvious because now there's no oxygen here. Reduction is loss of oxygen, can also be defined as that. Going this way, you're going up the number line, so this is oxidation. Alright? Okay. So alkanes are mostly used as fuel because they can be burnt. When they're burnt, they give off heat. Heat is used to heat up homes. And that process of combusting or burning alkanes is a process of oxidation. So oxidation plays a role in using natural gas to give you heat or to cook. Okay, so if there is sufficient air, you get CO2. If there is insufficient air, you get carbon monoxide, which is very toxic. You die of suffocation if you don't have a ventilated house. The other reaction other than oxidation that alkanes go through is halogenation. But because alkanes are are less reactive. Alkanes are less reactive. So we don't go through a regular mechanism. Instead, we go through radical mechanism. Okay. And that helps you to put halogens on the alkane, and that's why we call the reaction halogenation. So for example, assume you have an alkane, an R group. So for example, this, assume all this is the R group, the alkyl group. So that hydrogen can be replaced with a halogen. Okay. So let me just draw it here. It can be replaced with a halogen, where X could be a chlorine or a bromine, usually not fluorine, not iodine. So you will have replaced the hydrogen with a halogen, and the reaction is therefore said to be substitution reaction. You're gonna need harsh conditions, so you will want to heat or you want to use light energy to do this. So what happens if you have your alkyl group, an alkane, and then you have halogen? You know, halogens are diatomic, meaning two atoms making the halogen. Okay, two elements making the halogen. So these two, this and this will combine, and this will be added to the R. You're swapping, just swapping partners. That's how you'll end up with this. Okay, so the H and the X combines to give you HX, which could be HCl, HBr, depending on what you used as X2. So it's still substitution, whichever way you look at it, but it has to be radical mechanism. So there are three steps, basic steps involved. So your halogen of choice has to break apart. Remember, a bond is 2 electrons. So we move the 2 electrons. You get to make your first radical. So this is the first radical, first free radical. That's why the step is called initiation, because you're initiating the process. You're making your first radical. So again, specifically if your X is chlorine, so you move 1 electron this way. The fish hook means you're moving 1 electron, while the double arrow means you're moving 2 electrons. We talked about that in a previous chapter. So move this one here. So now the chlorines are radicals because they have unpaired electrons. Okay, so those radicals will be used to react in the next step. So now your alkane will come in to lose the hydrogen. So assume you have CH4, okay? So I'm just gonna expose 1 hydrogen, and you have your radical that you made in the initiation step. This is step 2, what we call propagation. So what happens is that the bond between the hydrogen and the carbon will break up. You know, it could be ethane, it could be isopropyl, it could be any alkyl group that has a hydrogen. We call that an alkyl group. But I'm just using the babyest alkane. So these two fish hook arrows meeting make the HCl. And then the CH3 will fall off as a radical. So you see, you're making another radical. So you're propagating, you're making more radicals. Okay, so you're propagating, making more is to propagate. So making more new radicals. So that CH3 could be represented by an R group. So it's an alkyl radical. This is an alkyl radical. The HCl is just a byproduct. Okay. Now, the newly formed alkyl radical, for example, your CH3 in this example, can break apart another molecule of your halogen, okay, by making a bond with one of the Cls. So that's how you'll get CH3Cl, and then this other chlorine of the diatomic chlorine molecule will make a radical. Okay, so this is an alkyl chloride. So you will have started with this, but you end up with this. Notice that you'll have substituted your H with a Cl. That's why we said the radical mechanism is a substitution reaction. Okay, so you formed another new radical. The characteristic of propagation is forming more radicals. Okay, characteristic of initiation is making the first radical from your halogen, making the first radical from your halogen. That's initiation. Propagation, you're making more radicals. Okay, let me clean up here. Here you're making more radicals. So you made a radical there, you made a radical here. And then this happens to be the product that we need. And then the next step, other than initiation propagation, is termination. So in termination, the characteristic of termination is no more radicals formed. In your products, no more radicals formed. Okay, so the two Cls that maybe broke out from this step, that and another radical can combine, because two electrons make a bond. They can combine. Remember, you use fishhook to bring together two electrons. You get back your halogen you started with, or your alkyl radical. For example, what I showed here, two of the alkyl radicals, because you keep making more, can combine. So if these two guys combine, guess what? You make, from your methane, you make your ethane. Okay. Alternatively, your methyl radical, alkyl radical, and halogen radical can combine. And that's how you make an alkyl halide, which will be the substitution product that would have been our interest. Okay. So that will be the reaction of alkenes with halogens. Okay. And after you substituted your first hydrogen, we started with CH4 with your chlorine. You ended up with CH3 with a chlorine and HCl. In other words, this thing lost one hydrogen. One hydrogen lost, replaced by the Cl. So you can keep replacing all the rest of the hydrogens if you keep doing the reaction. So this becomes your starting material. Okay, so you started with 3 hydrogens. You are doing halogenation in presence of UV light or heat. You'll be left with 2 hydrogens, and you brought in a second chlorine. Okay, so in other words, so to speak, this radical reaction can keep on replacing the hydrogens. So you did this, okay, which is this molecule. This molecule is this molecule, and then you can keep on doing the same thing. So you have chlorine, presence of UV light. That's just a sign of UV light. You can do the same second process again. Each time you make this new product, you're losing HCl. So 3 hydrogens, now you're left with 2, and you can keep doing it. And now do one more time. This time you're left with only 1 hydrogen, and then do it one more time. Okay, let me go back. I don't know what happened. So you're left with 1 hydrogen that you're about to lose it. Now you get tetrachloromethane. Okay, so it's stepwise halogenation. So if you don't keep the chlorine quite low, there's gonna be a mixture of all these products: monochlorinated, dichlorinated, trichlorinated, and tetrachlorinated. So tetrachloromethane, trichloromethane, dichloromethane, and monochloromethane. Those will be mixtures. So you really have to control the amount of chlorine you're using, otherwise it will keep on reacting. Okay. Alright, so I think I'm not going to talk about anything from this slide onwards. That will complicate things, as you can see. So that will mark the end of chapter 2. Now let's begin chapter 3. In this chapter, we'll discuss alkenes and alkynes, which are more reactive than alkanes. Alkenes is just a molecule having double bonds. For example, you see here limonene. I think if you've ever used menthol for your sore throats, that's the active compound. Okay, so generally alkenes will contain one single bond and one double bond, or one pi bond. So one of these will be sigma, we call it sigma, and the other one will be pi bond, not pi r squared that you use for circles. Just a pi is the name we give it because it's formed by side overlap of p orbitals. The sigma bond is formed by head overlap of s or p orbitals. Okay, the triple bond is gonna have 3 bonds. So one of these bonds, I usually pick the middle one, will be the strongest. We call it sigma. And then the 2 will be the pi bonds. Okay, they are the weaker one. They are the weaker ones of the 2. So they are used to react. Another name for these 2 classes, alkenes and alkynes, is olefins, but scientists threw away that name. That's an archaic way of calling them. But they are unsaturated because they have less hydrogens. What I mean is, for alkanes, you have this number of hydrogens. Alkenes, it's 2 hydrogens less. Alkynes is 4 hydrogens less compared to alkanes. That's why we say they are unsaturated. Okay, you've heard of unsaturated fats. They're called unsaturated fats because of presence of pi bonds. You want those because those are more reactive with your enzymes. They can be broken down. Saturated fats, they don't have pi bonds. They don't get easily metabolized in your digestive system. Then they accumulate in your body as fat, cholesterol, and you experience high blood pressure, obesity, and all those health problems. Okay, so because we are decreasing the number of hydrogens, it means that to make a pi bond, you have to lose a pair of hydrogens. That's why this number of hydrogens are going down. So for example, let me show you an example. If I have to make a double bond in this molecule, then I have to take out 2 hydrogens out of the 2 carbons. Okay, remember, each carbon must maintain 4 bonds. So that's what this statement is saying. For you to make a pi bond, you have to lose 2 hydrogens, what we call pair of hydrogen atoms. Yeah, I will not talk about the calculation of IHD, so I'm just mentioning that there's a formula to guess how many pi bonds you have or how many rings you have. But don't worry about the calculation part of that. It's a survey organic. The double bonds or the pi bonds can be arranged in different ways. If they are continuous, we call that cumulated. If they are in a pattern of double bond, single bond, double bond, single bond, or even triple bond, we'll call that conjugated, because you can draw resonances and push these double bonds around. Okay, if there is more than 2 sigma bonds between 2 double bonds, we call that isolated, because now these double bonds are isolated by the sigma bonds. Okay, the best, most reactive ones and most stable ones would be the conjugated systems, where you have pi, sigma, and so forth. Now, how is the length and bond angle? Usually, single bonds are longer than double bonds. Double bonds are longer than triple bonds. Okay, now in terms of bond angle, if you have a double bond, the bond angle is roughly, we say it is going to be roughly 120 degrees for alkenes. Why? The reason being that carbon in the middle is sp2 hybridized. Of course, we know sp2 hybridization relates to 120 degrees bond angle. Molecular geometry, I hope you've not forgotten, is trigonal planar. Okay. Again, the double bond has a length of about 1.34, which is shorter than the single bond. That's why I said single bond is longer than double bond is longer than triple bond. And the molecular geometry is trigonal planar. Looking at this shape, the whole molecule is sitting flat on the plane. Whole molecule is sitting flat on the plane. But again, if you connect the elements, it makes a triangle. That's why we call it trigonal planar. So you see, it's flat. It's flat. And this is just a cartoon showing you where the electron density is and where it's positively charged. So the brown area, the orangish area, is where it's electron dense. And obviously, it's going to be electron dense right in the middle because you have 4 electrons right there. That's why it's electron dense right in the middle in the double bond. You do have isomerism in alkenes. So one would look at what's bonded across. Okay, so cis means same side. If groups across the double on same side, that's cis. If groups across the double are opposite, that's called trans. For example, if I have metals on the same side like this, that's cis. But if the same metals are, sorry about that, if the same metals are opposite across the downboard, that's called trans. I think I mentioned that already in a previous chapter. So this is trans, where the CH3s are across the downboard. So alkenes do show isomerism. The problem is you cannot easily, if you try to rotate this, that will not happen unless you break it, which means these two guys are geometric isomers. We talked about that in the last class. You cannot interconvert them unless you break a bond. Okay, they are geometric isomers because a bond has to be broken for them to rotate. Double bonds don't really rotate along their axis. So again, this one is cis because I see the chlorines are on the same side across the double bond. This is trans because I see the chlorines are opposite. They are geometric isomers, cis trans isomers. If you compare them, this versus that, they are different. You can see the boiling point of this guy is 60 degrees. The boiling point of the trans is 47. The melting point is minus 80. The melting point here is minus 50. They have different physical properties, so they are different molecules because they have different dipole moments. You are asking, what is this dipole moments he's talking about? So if you point the dipoles towards the more electronegative element, that's how it looks like. So which means this guy is polar because they are not cancelling. But here, if I point it this way, those dipole moments are on the straight line and there's cancellation. So this molecule right here is non-polar. And because of that, you expect the physical properties to be different. Okay, like we said, you cannot rotate a cis to a trans without breaking a bond. This does not easily happen. You cannot rotate. So the best way to do this is first to break apart the bond because they're geometric isomers. If you really have to convert this to this, you break a bond. So use the 2 electrons and break them. We call this homolytic cleavage because you're moving 1 electron at a time. As you break the bond, you're cleaving it. And then now you have a chance to rotate what's left. You rotate the single bond that's left. So after the rotation, after doing the complete rotation, you end up here. And then now you reform your bond. Now you reform your bond. So you will have converted the cis to the trans. But guess what? We had to break the bond through this process. Okay. Now, what is the chemical reactivity? Usually alkenes and alkynes undergo addition reactions, which means you add elements or group of elements across the double bond, but that happens by sacrificing a pi bond. You'll be left with a single bond. So for example, you're starting with an alkene. Let's give a prototype diatomic element AB. So if A goes to this carbon, B will go to this carbon, but you sacrifice the pi bond because the weakest of the two, one of them is sigma, the other is pi. So after the reaction, you're only left with sigma as A and B are added. It's still addition because you added these two across. An example, the best example which is coming up is if you add the two hydrogens across the double bond, you're gonna end up with the hydrogens across and the hydrogen. So you'll have made an alkane while this was an alkene. That's one way of reducing alkenes to alkanes by a process called hydrogenation, which is coming up. That was instantaneous reaction. There's no formation of an intermediate we call a carbocation. But there are reactions where they will involve formation of carbocations, which is just a step in between your product and your reactant. Okay, so assume you have an alkene. This is not an equal sign, it's an alkene. In this case, this is ethene. So you can do what we call electrophilic addition mechanism, where the pi bond opens up. Remember, we are now using double-ended arrow. You're moving two electrons to pick up a positively charged element of this reagent. For example, this could be hydrogen, this could be Cl. Because of dipole moments, this hydrogen will be partially positive, which represents what we call the electrophile. The chlorine will be partially negative, which will fall off and come back as what we call as a nucleophile. So if the pi bonds picks up the E, which could be the hydrogen, and this falls off, you're gonna end up, you see how you had two hydrogens here? Now you're gonna end up with three hydrogens. Let's see. What? That's wrong. That's wrong. I needed to say. Now you're gonna end up with a plus charge with the two hydrogens. These two hydrogens here are these two hydrogens here, and a plus charge. Why do we need a plus charge? Because remember, you stole a bond from this carbon, and we said a carbon must have 4 bonds. See how we have 4 bonds, and we opened up this bond to pick up an electrophile. Okay, so this electrophile could be a hydrogen. So now if this was a hydrogen, you would have had CH3 here, but the other carbon will be 1 bond less, so to speak. Okay, and then this nucleophile, this Nu will be the Cl that will fall off. Okay, but that Cl will come as a nucleophile. A nucleophile means loves positive centers, so it's gonna come back and attack the positive center. So in which case, now I will have my CH2 there and my Cl, which is just given by this prototype. Now let me repeat. So the pi bond can open up, attacking the partially positive charge of the molecule, and then the other part falls off. You go through a positive charge species because now this carbon, for example, is 1 bond less. This species is called a carbocation because positively charged species are cations, but these are carbon bearing the positive charge. And then the nucleophile, the thing that fell off, will come back to attack. For me, I was assuming that I'm using ethene here to attack the hydrogen. The chlorine fell off, so I'll end up with the carbocation, which is this guy, and then the chlorine comes back to attack the other carbon. This hydrogen might have been this one that was brought in, and then you get your product. Okay, so it sounds very complex, but we'll soon expand on that more. So you realize we had to go through formation of a positively charged species, a carbocation. The more stable the carbocation, the most likely the reaction will go through it. So again, the more stable the carbocation, the most likely the reaction will go through it. In essence, carbocations are sp2 hybridized. The carbon C plus is sp2 hybridized. There's 3 electron domains. If this is sp2 hybridized, then it's trigonal planar. Okay. The most stable carbocation will be favored. What favors stability? These alkyl groups tend to donate electrons through bond. We call it electron donation by inductive effect. So you see how this guy has 3 alkyl groups. That helps to quench or neutralize the plus charge. That makes it more stable. So because you have 3 alkyl groups, we call it tertiary. This one has 2 alkyl groups, we call it secondary, which is less stable than the tertiary. The secondary is going to be more stable than the primary, and the primary is more stable than the methyl. There's no alkyl groups here. Okay, so it's easy to predict who will be formed based on the stability, which is the more substituted carbocation will be more stable. I'll ask you to rank that. So again, there's 2 ways of stabilization: inductive effect, where the alkyl groups are donating electrons through bond, or hyperconjugation. You see, this, we say that this carbon is sp2 hybridized, so which means there's going to be a p orbital which is missing compared to sp3. If you compare sp2 and sp3, sp2 is missing 1p. That 1p is empty. So the electrons in a bond nearby can be thrown in there. That will quench the plus character, and that's called hyperconjugation. It's called an orbital interaction between the adjacent CH bond that can overlap with the empty p orbital in the C+, which is this one, which minimizes the charge on the C+. So that's called hyperconjugation. So this one is a more fancy way of explaining the stability of the carbocation, but this is the most obvious one. But the 2 of them play a role in stabilizing the carbocation. But the same carbocations can be stabilized by resonance. So let's say you form this carbocation. You can push this bond here to end up with this resonance structure. That's the resonance contributing structure. We already discussed resonance in a previous chapter. So that helps to spread the plus charge around the molecule, and in fact you see that the central part will be more electron dense because the electrons go through the molecule. These electrons go through the molecule. Okay, that lowers the energy of the carbocation, making it more stable. There's also a situation where carbocations will undergo rearrangements, or what we call shifts, to be more stable. So which type of carbocation is this? I would show a bond here because I know carbocations will have 3 bonds. There's a hydrogen that's implied. This whole group will be called an alkyl group. There's a CH3 here. That's an alkyl group. So this guy is a secondary carbocation. Remember the ranking of carbocation. Tertiary is more stable than secondary. Secondary is more stable than primary. So if this is a secondary carbocation, we can move a hydrogen from a neighboring carbon that is more substituted. So this carbon is neighboring, this carbon is neighboring. Which one is more substituted? It's okay, these 2 carbons marked arrowed in red are neighboring to the one bearing the plus charge. So out of the carbons bonded to the C+, which one is more substituted? It's obviously this carbon, right? So we choose to move a smaller group from that carbon, which is this hydrogen. We do a shift. So we move it over there. And because you're moving a hydrogen, we call that hydrogen shift. As you move the hydrogen in the bond, the carbon here becomes one bond less. So it's one bond less. This carbon that was bearing the plus charge will now have two hydrogens. This hydrogen is this, and then this one is this. You no longer have a plus sign because now the carbon has 4 bonds. That CH3 is still there. So now look closely. What type of carbocation have we formed? This will be an alkyl group. That's an alkyl group bonded to the C+, and this whole mess here is an alkyl group. In fact, I would have clearly drawn it like that, so that this is an alkyl group, an alkyl group, an alkyl group. There are 3 of them. So now this whole structure, this whole molecule here is tertiary. So you'll have moved from a secondary carbocation to a tertiary carbocation. And that's what happens whenever carbocations can do a shift. They'll do it to be more stable based on this ranking. I will not go much into that details because as it looks, it's becoming complex. And this is survey organic, so I'm just mentioning shifts do happen. Now, apart from hydrogen shift, you have metal shift. Let me show you. What we just did is this. So suppose you have a plus sign here. That's a neighboring carbon, that's a neighboring carbon to the C+. This whole molecule is a secondary carbocation because I see there's a group there, alkyl group there, so it's secondary. So I can move this one here. Then I'll be left with the 2 metals, a plus sign because the bond is taken out, and then this is the hydrogen I moved. Okay, so now this became tertiary. This I call hydrogen shift. Now what if I have this? This time you always move a group from a neighboring carbon to the C+, which has more groups, so it's this carbon right here. If I move one of these CH3s right there, I still gonna have a vacuum. I call it a plus charge, and that CH3 is now here. So in other words, I can draw this as that. Okay, so again, I have 3 alkyl groups. So this is tertiary, but this guy was secondary. You'll have shifted from secondary to tertiary, but you moved an alkyl group. This is called an alkyl shift. Specifically, it's metal shift. So another example here is this. So suppose I have this ring here. Okay, it's secondary because that's an alkyl group going this way, this is an alkyl group going this way. This is still a secondary carbocation. That's what we're talking about, carbocations. I can move, you know, this is a neighboring carbon to the C+. This is a neighboring carbon from the C+. I move a baby group from the more substituted neighboring carbon. So here I have a CH3 and a hydrogen. I choose to move the hydrogen because it's easier to move small things. So in this case, we've done H shift or migration or rearrangement. So I'll be left with 1 bond less here. So the plus sign comes there. The hydrogen that was moved is now here. This was the original hydrogen. I moved this hydrogen. Now you see you have 3 alkyl groups across the C+. This is tertiary. Secondary to tertiary. Okay. Similarly, you can do a metal shift on this ring. If this bears a plus sign there, I move a group from the more substituted carbon, neighboring to the C+, which is this guy. This time I don't have hydrogens, I have metals, so I should do metal shift to create a more stable carbocation. The molecule will do this. So you'll be left with a vacuum there. The hydrogen is still here, but the methyl group migrated. So as you can see, focusing on the C+, that's an alkyl group. This is the rest of the alkyl group in the ring. That's the rest of the alkyl group in the ring. I have tertiary, so I would have converted secondary carbocation, okay, to a tertiary carbocation, and this is the guy that will continue with the reaction. All right, so that's all about carbocation shifts. Other than reaction involving carbocations, we have halogenation. So halogenation is usually used to test for, this is used to test for presence of pi bonds. In other words, it's used to test for unsaturation. Test for unsaturation, which is presence of pi bond. Now, like we explained before, or like I explained before, if you have a double bond, let's take ethene for example, and you add Br. This will go through addition reaction, and your CH2 will gain the Brs. The Brs will add it to the CH2s. Notice that you're losing the pi bond. You are left with only the sigma bond. This bromine molecule is red-brown, but after it reacts with the double bond, the solution you get will be colorless. That's exactly what's happening here. This is your liquid bromine. It's brown, but if you drop it, okay, if you drop the liquid bromine onto the alkene solution, so let's say this is an alkene, let's say this is this solution with a six-membered ring with a double bond, it's an alkene. If you add it to the alkene solution, what you get is the same colorless solution. As soon as the Br falls onto the alkene, the double bond reacts. So in this case, once the double bond reacts, you're gonna get alkyl halide. So you lost the double bond, or you lost the pi bond, so to speak. Okay. Okay, so you can see that the bromine, liquid bromine decolonizes. Okay. So that's the addition of bromine is a regular technique used to test for presence of double bond because you can't see them with your eye. What's the mechanism? So if you have ethene, one of the bromine will behave as the E part. Remember we had the E and Nu. The other one will behave as a nucleophile. So this will be partially positive, this will be partially negative. Okay, that's what's being shown on here. So the double bond the pi bond will be used to attack the Br. This falls off, and then in turn, one of the lone pairs of the Br will attack this carbon. So what you're doing is you're connecting this Br to this carbon, and then the Br is attacking the other carbon. So you're getting a three-membered ring. Remember, a Br will always have 3 lone pairs whenever it's bonded to something. So because you use this lone pair here to attack the other carbon, now what you have is 2 lone pairs. So you attack this Br, in turn attacks that carbon as this leaves. It leaves as a leaving group. So it's gonna come back and play the role of a nucleophile to pop open the three-membered ring. I told you three-membered rings are angle-strained. So it attacks from the other side. As it attacks this carbon, this opens up, neutralizing the plus charge on bromine. End up with a dihalogenated molecule called 1,2-dibromoalkane. So in other words, you started with ethene in presence of Br2, you get 1,2-dibromoethane. The pi bond reacted. Okay, so there are issues with this kind of addition reactions because you might end up getting mixtures, especially if the alkene is unsymmetric. So you see what we just used, this is this ethene that's symmetrical. So if you do a reaction with this, you expect just one product, which is this one. But when it's unsymmetrical, for example here now there's no symmetry. So in that case, you will have to follow a rule called Markovnikov to determine which is the major product, and that's what we call regiospecificity, regioselectivity. Okay, so the regioisomer, one of the regioisomers will be the major. You'll see that shortly. So again, let's say you have an unsymmetrical reagent reacting with an unsymmetric alkene. So for example, let's assume you have HCl. That's unsymmetrical compared to Br added on double bond. This is symmetrical. This HCl is not symmetric. So the question is, where will the H end up? Will it be on this or this carbon? And where will the chlorine end up? Will it be on this or this? So you realize if you add the hydrogen there and the chlorine here, losing the pi bond, this is what you'll get. So this would have been your hydrogen and this would be your chlorine. But you can do the other way around, where the chlorine and hydrogen goes opposite. You get this. But one of these will be the major. So you see the reagent elements end up on different regions of the molecule. So these two guys are called regioisomers. Okay. So the rule that we follow to determine which regioisomer is preferred out of these two, which of these two products is preferred, is called Markovnikov rule. So fortunately, there's a simple rule of thumb to predict or determine which product will be the major or which will be preferred, and that's Markovnikov rule, based on this Russian chemist called Markovnikov. Is a physicist, physical chemist. The Markovnikov rule states that when an unsymmetrical reagent adds to a double bond, the electrophilic part of the reagent adds to the carbon with the most hydrogens on it. Okay, too much stories, but what we mean is this. Assume you have an alkene which is unsymmetrical, like this guy. Okay, and you're adding unsymmetrical reagent like this. So the double bond attacks the hydrogen because the hydrogen is partially positive, chlorine is partially negative based on dipole moments. So the question is, where will this hydrogen go? This sp2 carbon has one hydrogen. This sp2 has two hydrogen. So according to Markovnikov rule, the hydrogen should add to the carbon with the most hydrogens on it. So where the hydrogen goes, where across the double bond to the sp2 carbon with more hydrogen, which happens to be this. So if you're attacking this hydrogen and this Cl falls off, that has to happen because that's what we've been doing. You attack the electrophile, the nucleophile falls off. You expect the CH2 to turn to a CH3 if you're to follow Markovnikov rule. And then this other carbon right here will be one bond less, and that's what makes us to give it a formal charge, because it's one bond less. If you do your formal charge calculations, this carbon will bear +1. If you do the opposite and put the hydrogen where there is less, then that hydrogen will come here, and which means the CH2 gets a plus charge. Now let's look at the ranking of these carbocations. Both of them are carbocations that I talked about before. Without showing the hydrogens, that's how that looks. You only have one alkyl groups alkyl group bonded to the carbon bearing the plus charge. So this is primary carbocation. In this case, if I draw without showing the hydrogen, then you have two alkyl groups, which is any carbon containing group bonded to the C plus. So you have two of them, so this is secondary. Remember our ranking will say tertiary carbocation is more stable than secondary, secondary is more stable than primary, primary is more stable than methyl carbocation. So this is more preferred because it's more stable than the primary, and it all happens because of Markovnikov rule, where the hydrogen went or ended up to the carbon bearing the carbon of the double bond bearing the more hydrogen. So that's Markovnikov rule. Again, Markovnikov rule states that when unsymmetrical reagent like HCl, HBr, HI adds to even water adds to a double bond, the electrophilic part, which is the H plus or the partial positive plus, because a partial positive part, because of dipole moment, this part will be added to the double bond, but it ends up on the sp2 carbon with the most hydrogens. So again, I repeat, if you had this, you have CH2 there, you only have one hydrogen here. So if you're adding anything like, let's say HBr for now, this hydrogen should end up here, the plus sign should end up there according to Markovnikov rule. So CH2 turns to be CH3 because that gives you the most stable carbocation. If you do the opposite, then you're gonna end up with primary carbocation. Okay? Because remember, you only have one hydrogen here. So if you add the hydrogen where there was less, you end up with that. This is primary. So this is the most favored regiocarbocation. So let's talk about specific reactions. The first one is hydration. Obviously, here you are adding H2O, or you're adding elements of water. You'll add a H and OH across the double bond, because H2O is just H and OH. Okay? Addition of water across the double bond. The product is alcohol, and it's made from an alkene starting material. Okay? It requires an acid catalyst because water is not very much of an electrophile. A perfect example is if you have CH2 of an alkene, and I give you H2O. So let me use here a color H2O. Okay. At the end of the day, so in presence of an acid catalyst, okay, at the end of the day, all you're adding is H and OH across the double bond. This alkene is symmetric, so there's no need to apply Markovnikov rule. So all I can do is to put the H and OH across the double bond, killing the pi bond. So OH will come here, the other H will come here. So in other words, this is the product. So you'll have started from ethene, and you make your beer, ethanol. So that's an example of hydration. You're adding elements of water across the double bond. Now, let's look at the mechanism. So this is your acid catalyst. So again, you're going to follow Markovnikov rule because now this alkene is unsymmetrical. It's different from what I just did. This guy is symmetrical. So we don't need to care about Markovnikov rule. So you have a H on that carbon, you have a CH2 on this carbon. So the acid catalyst proton should go where there is more, according to Markovnikov rule. The hydrogen goes to the carbon of the double bond that has more hydrogens. So this is a CH2. It turns out it's gonna end up being a CH3, and because you stole this bond from the other sp2 carbon, you get a plus sign. That hydrogen is still there, it's just not shown. And now your water can come in, playing the role of a nucleophile. It attacks the plus charge. You're gonna end up with this molecule. Again, the hydrogen is still there. CH3 is still there It's just not shown. That's not an alcohol. So a second molecule of water will come to steal the extra hydrogen and neutralize the oxygen. We don't want the charge on oxygen in an alcohol. So here you have 1 lone pair. After using these 2 electrons to donate to the oxygen, you will now have 2 lone pairs, and that will be your alcohol. This happens to be the rubbing alcohol that you buy in CVS, Walmart, Walgreens. It's isopropyl alcohol, otherwise called isopropanol. So this is one way you can make isopropanol using propene. Propene is one of the byproducts from oil refinery. Okay, so the other reaction is addition of HX. So you're adding a hydrogen and you're adding a halogen. The halogen here could be a Br, Cl, rarely F. It could also be an iodine. Okay. Whenever you're using HBr, it has to be done in the dark. Otherwise, you're gonna have the radical mechanism we talked about. The mechanism is the same. You have to follow Markovnikov rule, where the alkene is unsymmetrical. The hydrogen of the HX ends up where there is more. So similarly, I'm gonna ignore this for now because I want to show you. So let's say you're adding HBr. You have CH2, you have CH. So this double bond opens up, picking up a hydrogen. This hydrogen is gonna end up where there's more across the double bond, according to Markovnikov rule. This falls off. So you see, it fell off. The Br fell off as a leaving group. So this hydrogen is by itself. This carbon is 1 bond less. The CH2, after accepting this hydrogen, becomes CH3. That's a secondary carbocation. Instead of making a primary carbocation, if you do it the other way around, you have to follow Markovnikov rule. Br comes back to attack the plus sign because opposite charges attract. You get your 2-bromopropane. So far we talked about hydration. Now we talked about dihalogenation. We talked about hydration. Now we talked about hydrohalogenation. So if I give you a molecule like this and I tell you to add HCl, you have to think of Markovnikov rule. Show all hydrogens across the double bond. This hydrogen should end up where there is more, which is on this, and then the plus sign will go on the other side during the first step of the mechanism. So take out that hydrogen, this falls off. According to Markovnikov rule, I should end up with 2 hydrogens down here, and I should end up with a plus sign there, and then obviously the Cl fell off. So the Cl is lonely, is gonna come back with its negative charge to attack the positive charge because opposite charges attract, and then that's how you make your final product after following Markovnikov rule. So the Cl will end up here, the hydrogen will end up there. That is regio product, the preferred regio product. Okay, the other one is hydroboration. This is technically a hydration reaction, but you are using a specific combination of reagents, which is this. So typically you are just adding H and OH. That's the shortcut. The problem is this one will be anti-Markovnikov. So which means the hydrogen will end up where there's less hydrogens, OH will end up where there's more hydrogens across the double bond. So it's anti-Markovnikov hydration. Okay. So what happens? The BH3 aligns on top of the double bond, but the B will be on the side where you have more hydrogens. Okay. The H will be on the side where you have less hydrogens. That's the anti-Markovnikov curve. Okay, so we call this a transition state. So from this stage, one would expect that you'll have two hydrogens. This hydrogen, this is BH3. So this hydrogen will end up here. So you'll have two hydrogens, you still have your R group. And then across, you have the two hydrogens. But this bond breaks because you add this here. Your BH3 will lose the BH2 that attaches to the other carbon. Now, that is the first step. The second step, after adding BH3, the second step you use the peroxide and sodium hydroxide. So what happens is that this BH2 will be replaced by an OH. Will be replaced by an OH. So what are we seeing here? If you would have started with this molecule, let's say this was the molecule, and then you simply add H2O, hydration like we did, what would have expected is OH will go where there's less hydrogens, the hydrogen will end up where there's more. You see we have CH2, this would have been the product, okay? But now in our reaction in this slide, in hydroboration, we get the opposite regioisomer because we are using the BH3 as step number 1. Step number 2, we are adding hydrogen peroxide and sodium hydroxide. So this goes through a step where BH2 will be added on the other side, the hydrogen will add on the other side. Does not stop there. That's step 1. Okay, step 1 gives you that. Now step 2 will replace the BH2 with an OH. So these two alcohols are different. Can you see that they are different? This is 2-propanol, but this one is just the normal propanol. This is 1-propanol. They are different. Because why? Anti-Markovnikov addition. So that's what's shown on here. Oh, something stuck in my mouth. So that's what's shown on here. This hydrogen goes where there's less. The BH2 goes where there's more hydrogens. That's anti-Markovnikov addition. And then you keep on repeating until these hydrogens are replaced by R group. But at the end, you add your peroxide. So don't worry about all this mechanism. Just know once you have this group, that's going to be switched with an OH at the end. That's the shortcut I want you to know. So instead of having this product, you'll have this product. That's the anti-Markovnikov. I won't ask you about the mechanism. Just remember the comparison I did. So let me give you examples here for hydroboration because that's a little bit complex. Okay, so let's assume you have this ring and I tell you to react it with water in place of an acid. Very well, you'll know that the hydrogen will go here, the OH will end up there. That's what hydration is. This is hydration following Markovnikov rule. Okay, it gives you the most substituted alcohol. So losing the pi bond, that will be my product. But if I take the same molecule and subject it to hydroboration, which use just BH3 step 1 and then hydrogen peroxide, sodium hydroxide, this one will give you the opposite. OH will come here. Here the hydrogen went there, OH went here. That's the shortcut to do it. But for this one, the hydrogen will go there, OH will go here. So the product will be switched regiochemistry. So your hydrogen will be here and then your OH will be there. So these two guys are regioisomers. Why? Because hydroboration is an anti-Markovnikov reaction where the hydrogen of the reagent ends up where there's less across the double bond. Okay, this hydrogen ends up where there's less. There's no hydrogen here, there's one hydrogen there. So it's doing the opposite of what we knew up here. So anti-Markovnikov addition. That's the reason why you get these regioisomers. So next we'll talk about hydrogenation next time.